Electrostatics is a study of electric charges that can be collected and held in one place. This is where electricity all begins. Okay. Now, um, if you need more advice and more help, of course, may I suggest you check out the textbook. So in nature, there are two kinds of charges. There's the positive charge and a negative charge. Okay, and an electric charge is a carrier. Um, if we have a positive, it's going to be a proton, and if we have an electron, it'll be negative. Now, neutrons are neutral; they do not hold a charge. Okay, you're going to see that the proton and the neutron ends up being part of the nucleus of an atom. Electrons float around in outer layers. Okay. A body that is neutral has no charge. In order for a body to be neutral, or for an atom to be neutral for that matter, that means that the number of protons in the nucleus is the same as the number of electrons floating around the atom. So the number of protons would be the same as the number of electrons.
That's all there is to it.
Problem 1, net charge. So we have a gram of matter that has 10 to the 23rd positively charged protons. How many electrons are there? Now, we're going to assume that this material is neutral. Okay? Now, if it's neutral, then the number of protons is the same as the number of electrons. So if there are 10 to the 23rd protons, there will be 10 to the 23rd electrons. Okay? What is the net charge? Well, the net charge means, is there a balance? In other words, do we have more protons or do we have more electrons? In this case, because it's neutral, there is no net charge. The net charge is 0. Okay, it's balanced. It's neutral. All right. However, if we were to go ahead and charge this object and either remove electrons or add electrons, then you would notice that there would actually be a net charge that would be in either direction. In an uncharged body, what can be said about the number of protons and electrons? Well, if it's uncharged, that means that it's still neutral. And if it's neutral, that means it's not extra positive or extra negative. It's just balanced. It's in equilibrium. So that means that the number of protons would be equal to the number of electrons. However, if we want to go ahead and charge a body, we're going to go ahead and apply it to friction or rub it, or perhaps we may add an electrical source to it. We're going to change the charge by either adding or removing electrons. We don't make items positive by adding protons, even though we are thinking that in order to make something positive, we would add protons because they're positive charges. Not quite the contrary. If you're going to go ahead and make something positive, you would remove electrons from it, and that would leave you an excess amount of positive charges, and that would make it positive. If I wanted to make something negative, I would go ahead and add electrons to it. So what actually happens when they charge a body, when we rub it or expose it to extra charge, we are messing with the number of electrons. We are transferring electrons back and forth. So when we're rubbing an object, right? When we're trying to when we're rubbing the balloon on the sweater or on our hair or whatever, that action of friction is removing electrons, okay, or adding electrons. What's actually happening is we are moving electrons around back and forth. If electrons are removed, then the object becomes positively charged, and if electrons are added, the object becomes negatively charged. Problem 3, copy machines. So there are carrier beads in a Xerox copy machine. These are actually patented, and they are covered with toner particles that cling to it. So this makes it so that the machine doesn't pump out all this powder, because Xerox copy machines don't actually have ink. They use powder. We call it toner. Okay. What makes these particles cling to the bead? The carrier beads are positively charged, and the toner particles are negatively charged. So it's a very convenient match because they're going to attract to each other. Oppositely charged objects will attract to each other. So in other words, if we have a positive and a negative, or we have a negative and a positive, these are forms of attraction. Repulsion, a repulsive force, is if we have a positive and a positive, or a negative and a negative. This is the nature of charges. Okay, so the copy machine, the zeros copy machine works because of this principle where opposites are going to attract. Summary: what can be done to give something a positive charge? A material through which a charge does not move easily is called an electric insulator. May I suggest to you that insulators tend to guard electrons. They tend to be possessive. They tend to be stingy. Okay, they is not that insulators do not carry charge. Okay, it's not that insulators must be neutral. They can definitely be negatively charged. They can definitely be positively charged. They can definitely transfer electrons. Insulators can transfer electrons. They do. They do transfer electrons. However, it's not as easy, right? So if you find yourself having to rub something to charge it, most likely it might be an insulator. Insulators tend to is a material that tends to keep charge localized, meaning that it stays in a certain area, right? So if I rub the balloon on my hair, it's the area that I rubbed the balloon where the charge is going to be. It's not going to be spread out through the entire balloon. It'll stay localized, okay? However, if we have a conducting material allows the charges to move easily. They're not stingy. They're very free-flowing. They allow it to just go right through them, okay? So a conductor would freely share electrons. A conductor, if you touch one part of a conducting material with the charge, the rest of it is going to charge automatically. Okay, it's almost like catching on fire. Okay, except I'm talking about figuratively here. So if you're finding that a material is a conductor and it got charged at one point, it will be charged at all other points at the same time. Okay, the charge gets spread out on a conductor. It doesn't stay localized. Conductors and insulators. So let's go ahead and show you a couple of drawings. In the left, we have a conductor, and on the right, we have an insulator. And we have this, let's call it a sphere, right, or a ball or some shape. And here's a rod. And I'm going to go ahead and charge this rod, and it's going to be negatively charged. Okay? This is a negatively charged rod. That's why I put these little negatives on there, electrons. If this is a conductor, when I go ahead and touch this part of the sphere, these electrons leave the rod and they go ahead and transfer to not only this spot, but they transfer evenly to the rest of the conductor. So even though I've only touched this point right here, this part of the conductor, it ends up spreading out throughout the entire item. Okay, that's what a conductor does. It releases, it accepts, it allows for electrons to travel very freely. All right, so I didn't have to touch the entire sphere. I touched it in one spot, and because it's a conductor, the entire sphere got the charge. Okay, now when we look at an insulator, if I touch this spot right here, I'm going to lose some electrons, and the electrons are going to stay local to the region that they were touched. Okay, it did not spread out through the entire sphere. Insulators do not do that. Okay, so there's pros and cons to this, right? Sometimes you want charge to flow freely and easily. Sometimes you want it to stay localized. All right, that's what a conductor and an insulator do. What are some cases where a conducting material might be beneficial? What are some cases where an insulator might be beneficial?